Hi everyone. So welcome to the Young Stars program. Whether you're a regular attendee or tuning in for the first time, we're thrilled to have you with us today. So I'll be sharing some of what we know about antimatter. And perhaps the first thing to say about antimatter is that there are many things we don't know. It seems there are many secrets of antimatter that are yet to be discovered. Antimatter is very hard to work with in the laboratory, and I will explain why we have so much trouble. But first we must ask, what is antimatter? Imagine that this apple is one of the fundamental particles, the very smallest things in our universe. What properties does it have? How would you describe it? What makes an apple an apple? So send me your ideas in the chat. How would you describe an apple? Red, fruit, awesome. A piece of matter, it is indeed. It's made of molecules. Colored, it's juicy. Awesome. This was my list. Sweet, red, tasty, and as the saying goes, an apple a day keeps the doctor away. So an apple is made of regular matter, as you guys identified, which makes up the things we see and touch every single day. Antimatter is defined by having certain properties the exact opposite of regular matter. So with the properties of the apple that you've just defined, can you tell me now what the opposite of those would be? What do you think an anti-apple would look like? Sour, dead, inedible. These are all really good. Orange, awesome. These are really good ideas, and it's quite hard to define opposites for some of these things, really, like color. It doesn't have a clear opposite, so you guys have done very well. This was my attempt. So now that we have matter and antimatter being the opposite of each other, what happens if we bring two opposite things together? What happens if matter and antimatter collide? Does anyone have any ideas? Send them through in the chat. It explodes, explosion, nothing, it cancels out. Yeah, opposites cancel, they cancel. Half of each. These are really great ideas, great predictions. Everything turns into antimatter. Yeah, maybe one could be dominant. All great ideas. Thank you. So it turns out that when matter and antimatter meet, they annihilate each other, leaving no trace of either one. But this does release lots of energy in the form of light. This is what Albert Einstein discovered with his most famous equation, E equals mc squared, which tells us that mass, m, can be converted to energy, E. And this letter C, the speed of light, which is very, very fast, tells us that there is lots of energy in anything that has mass. So an apple weighs about 100 grams, and if we smashed it together with our hypothetical anti-apple, it would release lots of energy, in fact, enough to power Australia for a whole year. So all of the physics we understand today tells us that the Big Bang at the beginning of the universe should have created an equal amount of matter and antimatter, opposites equally balanced. However, when we look into space at our universe, we barely see any antimatter at all. The regular matter we are familiar with seems to dominate wherever we look. So why is there more matter than antimatter? Now I'm going to skip to the answer on this one because we don't really know. This is one of the biggest questions in physics, and almost everything that particle physicists do is related to answering this question. And there are broadly two major efforts to answer this question, but both are very important. The first is to search for new laws of physics, something better than the standard model, which is currently the very best description we have of the smallest things in our universe. This is done at the Large Hadron Collider at CERN in Switzerland, which some of you have probably heard of. They send tiny particles around a 27-kilometer circular loop, and it's about 100 meters underground. When the particles smash together, they can create conditions like the universe in the moments after the Big Bang. The other approach is to better understand antimatter. And perhaps there are strange ways that antimatter behaves differently to regular matter. So experiments like the alpha G shown here, which is also at CERN, they trap lots of antimatter in their laboratory, and then they can study it very closely. This is the area that I want to focus on to tell you how scientists create antimatter and why it can be so difficult. So, of course, in reality, we do not find anti-apples in nature, but the same ideas that we just discussed apply to the smallest objects in our universe, the fundamental particles. Let's start with the apple. What is it made of? If we zoom in about 100 million times, we find molecules. This is a sugar molecule. It is a collection of carbon and hydrogen and oxygen atoms. An atom, about 10 times smaller, contains electrons. And these electrons are buzzing around a tiny nucleus at its center. These electrons are among the fundamental particles, the very smallest things we know of. Zooming in 10,000 times again, the nucleus is a blob of protons and neutrons. And these protons and neutrons are each made up of 3 quarks. Quarks, just like electrons, are fundamental particles, the very smallest things. The one you see here are called up and down quarks. Every fundamental particle has an antimatter form as well. If we put lots of these together, then of course we could begin to make atoms and molecules of antimatter, but we usually have enough trouble getting to the particles just on their own. So here is an electron. It is regular matter. It has a negative electric charge, which means that 2 electrons will repel each other because like charges repel. As you know, antimatter is all about opposites. So this positron here, the antimatter partner of the electron, it has a positive electric charge. And this means that 2 positrons will also repel each other. Not all properties are opposite though. In many other respects, the positron and electron are identical. For example, they have the same mass. If we bring the electron and positron together, they annihilate, releasing energy in the form of an extreme type of light called gamma rays. So to do experiments in the laboratory with antimatter, we must be able to control it. Magnets have many useful applications, and you'll probably be finding them on your fridge, and they also enable high-speed trains. In the laboratory, we use magnets to bend particles that have a positive or negative charge. Here, we have a magnetic field pointing upwards. Let's take an electron, and I want you to guess whether this magnetic field will bend the negative electron towards person B, who is standing in the distance, or person A, who is standing very close to us. So have a guess and send your ideas in the chat. Will the electron move towards person B in the distance or person A close to us? Go, great mix of both options. The answer is it bends towards person B. So now let's take a positron. Which way do you think it will bend? Let's find out. The opposite. So the positron has a positive charge, so it goes in the other direction. And this magnetic field gives us a way to control very small particles so that we can do experiments with them. But there is something else we need if we are to learn about these very small particles. we need to see where they are. We need to keep track of them. So tell me in the chat if you have any ideas about how we can see these tiny particles like electrons and positrons. Does anyone, a microscope, a telescope, antimatter telescope? Lots of people saying microscope. So microscope is great because it allows us to zoom in on something. And with a traditional microscope that we look through, we're using light to see other objects. And so because when we go to things very, very small like particles, we need some other ideas as well. So somebody's got electron microscope. So we can apply the principles of a microscope to some other device. Great, thanks for all the ideas. There are definitely so many ways to track tiny particles. So I'm just going to talk about one. This is something that I'm sure you've all seen in the sky, cloud trails left by aeroplanes. They fly very high in the sky, making the planes themselves very hard to see. But these cloud trails make them easier to find and even tell us where the plane has been flying for the past hour or so. We can use a very similar idea to track small particles. So firstly, how do clouds actually form? Liquid water is heated by the sun and evaporates into a vapor that rises into the sky. And as it becomes colder, dust in the sky can create instabilities that cause droplets to form. And these droplets collectively produce a cloud. So in the laboratory, we can use cloud chambers, and they are filled with a special vapor. And when a charged particle like a positron travels through the vapor, it creates instabilities just like the dust, just like the aeroplane, which cause droplets to form. This leaves a nice track showing the path of the positron. And in this image to the left, you can see some of these particle tracks inside a bubble chamber, which works in a very similar way. If we zoom into these green swirls, this can be explained by the production of an electron and positron with the reverse of annihilation. Gamma rays can actually create an electron-positron pair. There is a magnetic field here as well, which is pointing out of the screen towards us. And so just like I showed you before, with the particles bending towards person A, bending towards person B, the electron and positron swirl in opposite directions. So now we have a way to control antimatter, and we have a way to see antimatter. Antimatter was first discovered in one of these cloud chambers, but now we have lots of other tools as well. The question we must now ask is, how do we actually make antimatter so we can use it in our experiments? And of course, where do you make things? In a factory. This picture is real, and it's what they call one of their facilities at CERN. They have particle accelerators and lots of other big machines which are used to make antiprotons. Also located in Switzerland is the Paul Scherrer Institute, which uses this huge particle accelerator to send protons smashing into a block of carbon, which spits out a variety of antimatter particles. And one of the big mysteries of antimatter that both facilities are trying to solve is how antimatter behaves under gravity. The story goes that Isaac Newton thought of his law of gravity when he saw an apple fall to the earth from a tree in Cambridge. We experience this every moment, really, because matter, including ourselves, falls down towards the earth. But if antimatter is all about opposites, then does that mean that antimatter falls up? So this seems like a very simple question, but in fact it has never been answered by experiments because we only create very small amounts of antimatter, and there are lots of challenges for using antimatter in the laboratory. So how do we measure gravity? Well, we know that the Earth, being so massive, has a gravitational pull. For regular matter, if we watch it fall over a given height and record the time it takes, then we can determine the strength of gravity that was acting on it. Most physics theories do assume for now that antimatter responds the same way as matter under gravity. This assumption does seem consistent with some physics, but we still have never been able to test it experimentally. It's possible that the gravitational pull of the Earth, which is made of regular matter, has a weaker effect on antimatter. It could even have the opposite direction, creating a repulsion of matter and antimatter, so pushing them apart. So, in order to test this, we could take a positron, for example. But the positron has a positive electric charge, and our world, including laboratories, is filled with electromagnetic signals, electric devices, and other charged particles, which create electric fields and magnetic fields that are much stronger than the effects of gravity. So if we watch the motion of a positron, any effects of gravity from falling under gravity would be washed out by these dominant electromagnetic forces. So what we can do is to combine the positron with something negatively charged, an electron. They can be combined in a special configuration such that the positive and the negative cancel out to zero. We call this neutral, so it has no charge. And now it will not be affected by the electromagnetic forces. And an experiment at the Paul Scherrer Institute uses this approach, but instead of the positron, they use an anti-muon. You can think of this as the heavy cousin of the positron. It's very similar, but has a much, much larger mass. So we can observe its motion under gravity as follows. But oh no, what's happened here? The muon only lives for a very short time after we make it, and then it explodes into a mix of other particles. So this means that it experiences gravity for a very short time. And the amount that it moves under gravity, as you saw in this animation, it's very, very small. And that makes it extremely hard to measure. It's very hard to measure how the antimatter is responding to gravity. So we can make antimatter, and as I've just shown you, we can transform it into a neutral form so that the effects of gravity by itself can be seen. But because these effects are so very small, we need to repeat the process many, many times. And this is quite common in science, where we need to watch something over and over again in order to understand the average behavior. So in 2018, I was involved in an experiment at the Paul Scherrer Institute to work on new ways to make this neutral combination of anti-muon and electron, which we call muonium. And we found some new materials that can be used to produce lots of it, enough so that hopefully a gravity measurement will become possible in the near future. So, as I've shown you, there are many challenges in answering this simple question: does antimatter fall down or fall up under gravity? The answer may be that it behaves exactly the same as matter, but it is such an important question that it must be tested. For anything in science, really, we must ask nature for the answer. We must do experiments to test our ideas. Antimatter is a very elusive substance with many secrets that are yet to be discovered. Understanding more about antimatter will help us to answer some of the biggest questions in physics about how the universe actually began. And much of particle physics can be traced back to this question: why is there more matter than antimatter in our universe? This is a big question that I think will require many different scientific discoveries well into the future, before we'll be able to answer it. And perhaps some of the young stars joining us today will one day be part of those discoveries.